After World War I, the United States Department of Defense created a unique approach to safety that they called system safety. The United States started to build nuclear weapons, early warning and launch on warning systems, and intercontinental ballistic missiles. The consequences of accidents in these systems were so enormous that safety had a very high priority. Some defense systems, such as atomic weapons, can potentially have such catastrophic consequences that they must not be allowed to behave in a non-safe fashion under any circumstances. The accidents were unthinkable. At the same time, the complexity of these systems was orders of magnitude greater than previously attempted, and the inadequacy of previous approaches to safety engineering was dramatically illustrated in close calls. Something new was needed. Much of the early development of system safety as a separate discipline in the defense industry began with flight engineers after World War II. The Air Force had long had problems with too many aircraft accidents. For example, from 1952 to 1966, it lost 7,115 aircraft, in which 8,547 people, including 3,122 pilots, were killed. Most of these accidents were blamed on pilots. Some industry aeronautical engineers, however, did not believe the cause was so simple. They argued that safety must be designed and built into aircraft, just as are performance, stability, and structural integrity. This was the beginning of a unique systems approach to safety. Seminars were conducted by the Flight Safety Foundation, headed by Jerome Lederer, who would later head the NASA Apollo Safety Program, that brought together engineering, operations, and management personnel. It was in 1954 at one of these seminars that the term system safety may have first been used in a paper by one of the aviation safety pioneers, C.O. Miller. Around the same time, the Air Force began holding symposiums that fostered a professional approach to safety in propulsion, electrical, flight control, and other aircraft subsystems. But they did not at first treat safety as a system problem. When the Air Force began to develop ICBMs, intercontinental ballistic missiles, there were no pilots to blame for accidents, yet the liquid propellant missiles blew up frequently and with devastating results. The missiles used cryogenic liquids with temperatures as low as 320 degrees Celsius and pressurized gases at 6,000 LABs per square inch, which meant the potential safety problems could not be ignored. The highly toxic and reactive propellants were sometimes more lethal than the poison gases used in World War II, more violently destructive than many explosives, and more corrosive than most materials. The Department of Defense and the Atomic Energy Commission, AEC, were also facing the problems of building and handling nuclear weapons and finding it necessary to establish rigid controls and requirements on nuclear materials and weapon design. Most of the development of system safety as a unique discipline grew out of these nuclear weapon and ballistic missile programs. In that same period, the AEC and later the Nuclear Regulatory Commission, or NRC, was engaged in a public debate about the safety of nuclear power. Similarly, civil aviation attempted to reduce accidents in order to convince a skeptical public to fly, and the chemical industry was coping with larger plants and increasingly lethal chemicals. These parallel activities resulted in different approaches to handling safety issues, as described previously. Little cross-fertilization between these approaches occurred, partly because many of the features of system safety were not known outside the small group of engineers and companies that worked on these very secret Cold War systems. The system safety approach developed for them is no longer secret, but it is largely unknown outside the United States or even by many safety practitioners in other industries within the United States. In the 50s, when the first missile systems such as the Atlas and Titan ICBMs were being developed, standard safety approaches were used. Intense political pressure was focused on building a nuclear warhead with delivery capability as a deterrent to nuclear war. In an attempt to shorten the time between initial concept definition and operational status, a concurrent engineering approach was developed and adopted. In this approach, the missiles and facilities in which they were to be maintained ready for launch were built at the same time that tests of the missiles and training of personnel were proceeding. The Air Force recognized that this approach would lead to many modifications and retrofits that would cost more money. But with nuclear war viewed as the alternative, they concluded that additional money was a cheap way to buy time. A tremendous effort was exerted to make the concurrent approach work. On these first missile projects, system safety was not identified and assigned as a specific responsibility. Instead, as was usual at the time, each designer, manager, and engineer was assigned responsibility for safety. These projects, however, involved advanced technology and much greater complexity than had previously been attempted, and the drawbacks of the standard approach to safety became clear when many interface problems went unnoticed until it was too late. Within 18 months after the fleet of 71 Atlas F missiles became operational, 4 blew up in their silos during operational testing. The missiles also had an extremely low launch success rate. An Air Force manual describes several of these accidents. An ICBM silo was destroyed because the counterweights used to balance the silo elevator on the way up and down in the silo were designed with consideration only to raise a fueled missile to the surface for firing. There was no consideration that when you were not firing in anger, you had to bring the fueled missile back down to defuel. The first operation with a fueled missile was nearly successful. The drive mechanism held it for all but the last 5 feet when gravity took over and the missile dropped back. Very suddenly, the 40-foot diameter silo was altered to about 100-foot diameter. During operational tests on another silo, the decision was made to continue a test against the safety engineer's advice when all indications were that because of the high oxygen concentrations in the silo, a catastrophe was imminent. The resulting fire destroyed the missile and caused extensive silo damage. In another accident, 5 people were killed when a single point of failure in a hydraulic system caused a 120-ton door to fall. In general, launch failures were caused by inadequate requirements, design flaws, construction errors, for example, reverse gyros and reversed electrical plugs, bypass of procedural steps, and management decisions to continue in spite of contrary indications because of schedule pressures. Not only were the losses themselves costly, but the resulting investigations detected serious deficiencies in the systems that would require extensive modifications to be corrected. In fact, the cost of the modifications would have been so high that a decision was made to retire the entire weapon system and accelerate deployment of the Minuteman missile system. Thus, a major weapon system originally designed to be used for a minimum of 10 years was in service for less than 2 years, primarily because of safety deficiencies. When the early aerospace accidents were investigated, it became apparent that the causes of a large percentage of them could be traced to deficiencies in design, operations, and management. The emphasis for such systems began to be on building them to be safe from the beginning. In this approach, hazards are identified in the early stages of system development and then eliminated in the system design. A fly-fix-fly approach was clearly not adequate. In this approach, investigations are conducted to resurrect the causes of accidents. Action is taken to prevent or minimize the recurrence of accidents with the same cause, and eventually these preventive actions are incorporated into standards, codes of practice, and regulations. Although the fly-fix-fly approach was effective in reducing the repetition of accidents with identical causes, it became clear to the Department of Defense, DoD, and later others, that it was too costly and, in the case of nuclear weapons, unacceptable. This recognition led to the adoption of a safety system approaches 60 to 70 years ago to try to prevent accidents before they occur the first time. The first military specification on system safety was published by the Air Force Ballistic Systems Division in 1962, and the Minuteman ICBM became the first weapon system to have a contractual, formal, disciplined system safety program. From that time on, system safety received increasing attention, especially in the Air Force missile programs, where testing was limited and accident consequences serious. The Army soon adopted the system safety programs developed by the Air Force because of the many personnel it was losing in helicopter accidents, and the Navy followed suit. In 1966, the DoD issued a single directive requiring system safety programs on all development or modification contracts. First, there were a few techniques that could be used on these complex systems, but step-by-step scientific, technical, and management techniques were developed or adapted from other activities. Contractors were required to establish and maintain a system safety program that was planned and integrated into all phases of system development, production, and operation. A formal plan was required that ensured that 1. Safety consistent with mission requirements is designed into the system. 2. Hazards associated with the system, each of the subsystems, and the equipment are identified, evaluated, and eliminated or controlled to an acceptable level. 3. Control over hazards that cannot be eliminated is established to protect personnel, equipment, and property. 4. Minimum risk is involved in the acceptance and use of new materials and new production and testing techniques. 5. Retrofit actions required to improve safety are minimized through the timely inclusion of safety engineering activities during the acquisition of a system. And 6. The historical safety data generated by similar programs are considered and used where appropriate. To summarize all of this, the primary concern of system safety is the management of hazards, their identification, evaluation, elimination, and control through analysis, design, and management procedures. Losses in general, not just human death or injury, are considered. Such losses may include destruction of property, loss of mission and environment, mental harm. The key point is that the loss is considered serious enough that time, effort, and resources must be put into preventing it. How much of an investment is considered worthwhile to avoid the loss or its effects will depend on social, political, and economic factors. System safety activities start in the earliest concept development stages of a project and continue through design, production, testing, operational use, and disposal. The primary emphasis is on the early identification and classification of hazards so that corrective action can be taken to eliminate or minimize their impact before final design decisions are made. To understand the unique aspects of the system safety approach and differentiate it from the other approaches to safety developed in parallel but independently for such industries as civil aviation and nuclear power, a few basic unique concepts can be identified. System safety emphasizes building in safety, not adding it on to a completed design or trying to assure it after the design is complete. 70 to 90% of the design decisions that affect safety will be made in the concept development project phase. The degree to which it is economically feasible to eliminate a hazard rather than to control it depends on the stage in system development at which the hazard is identified and considered. Early integration of safety considerations into the system development process allows maximum safety with minimal negative impacts. The alternative is to design the system or product, identify the hazards, and then add the protective equipment to control the hazards when they occur, which is usually more expensive and less effective. Waiting until operations and then expecting human operators to deal with hazards is the most dangerous approach. System safety deals with systems as a whole rather than with subsystems or components. Safety is a system property, not a component property. The hazards associated with an individual component, such as sharp edges, are very different than the hazards that arise when all the components operate together. System safety takes a larger view of hazards than failures. Serious accidents can occur while system components are all functioning exactly as specified, that is, without failure. If failures only are considered in a hazard analysis, many potential accident scenarios will be missed. In addition, the engineering approaches to preventing failures, increasing reliability, and preventing hazards, increasing safety, are different and sometimes conflict. System safety emphasizes analysis rather than past experience and standards. Standards and codes of practice incorporate experience and knowledge about how to reduce hazards, usually accumulated over long periods of time and resulting from previous mistakes. While such standards and learning from experience are essential in all aspects of engineering, including safety, the pace of change today does not allow such experience to accumulate and for proven designs to be used. System safety analysis attempts to anticipate and prevent accidents and near misses before they occur. System safety emphasizes qualitative rather than quantitative approaches. System safety places major emphasis on identifying hazards as early as possible in the design stage and then designing to eliminate or control those hazards. In these early stages, quantitative information usually does not exist. In addition, our technology and innovations are proceeding so fast that historical information may not exist or may not be useful. Some components of high technology systems may be new or may not have been produced and used in sufficient quantity to provide an accurate probabilistic history of failure. The accuracy of quantitative analysis is also questionable. The majority of factors in accidents cannot be evaluated in numerical terms, and those factors that can be quantified will often receive undue weighting in decisions based on absolute measures, while those that cannot be quantified are ignored. Finally, quantitative evaluations usually are based on unrealistic assumptions that are often unstated, such as accidents are caused by failures. Failures are random. Testing is perfect. Failures and errors are statistically independent. And the system is designed, constructed, operated, maintained, and managed according to good engineering standards. Surprisingly, few scientific experiments have been performed to determine the accuracy of probabilistic risk assessment, particularly considering the length of time they have been used. The results of the few scientific experiments that have been done, however, have not been encouraging. System safety recognizes the importance of trade-offs and conflicts in system design. Nothing is absolutely safe, and safety is not the only or usually even the primary goal in building systems. Most of the time, safety acts as a constraint on how the system goals, mission, can be achieved and on the possible system designs. Safety may conflict with other goals, such as operational effectiveness, performance, ease of use, time, and cost. System safety techniques focus on providing information for decision-making about risk management trade-offs. System safety is more than just system engineering. System safety concerns extend beyond the traditional boundaries of engineering to include such things as political and social processes, the interests and attitudes of management, attitudes and motivations of designers and operators, human factors and cognitive psychology, the effects of the legal system on accident investigations and free exchange of information, certification, and licensing of critical employees and systems, and public sentiment. The systems approach to safety engineering described in this book and in Engineering a Safer World incorporates and extends this traditional defense system safety approach.